All right, in this video, we're going to have a look at periodic models. So here we're using sinusoidal curves, sine curves, and cosine curves to model situations that have behavior that matches these functions. Okay, there are many situations actually that a model using a sine or cosine curve is appropriate. Tides are examples, lunar orbits, springs, and sort of a fun one, Ferris wheels. So we're going to start off with the Ferris wheel problem. This is a fairly common type of problem in high school math. So here it is. Using a sine function, and I put it at the bottom, note we could also model this using a cosine function, but I've just made the question so it specifies which one we'll use. Using a sine function, model the height of a person who gets on a Ferris wheel at time 0, where the Ferris wheel has a diameter of 100 meters, is 5 meters above the ground, that is the place where the person gets on, and takes 36 minutes to make one full revolution. Okay, so we want to come up with a function involving sine that tells us where the height of this person is at any given minute starting at time 0, and I guess until the completion of this person's ride at 36 minutes. All right, well, so first of all, we have that we're going to have y equals a sine q onto x minus h plus k. Okay, that's just the sine curve with the 4 parameters put in. And we want to systematically figure out the values of these parameters. Now, I made a mention actually in a previous video that in such questions, I personally will usually use the strategy of using the information that's given to me to find A, Q, and K, and then find a point that I can plug in to solve for H. Usually that approach will work. Not always, you might have to think on your feet, but often that will be a good way to go. So I'm just going to go through step by step and see what information I have. So we're going to model the height of a person who gets on a Ferris wheel at time 0. So they get on at time 0, on at time 0, where the Ferris wheel has a diameter of 100 meters. Okay, let's stop there for a second. It has a diameter of 100 meters. What does this mean? It means that this huge Ferris wheel has a diameter that looks like that. Okay. It's 5 meters above the ground. Okay, so what does that mean? That means that this point here, whoops, give me back my circle. This point here, right here, one more try. There, right there is 5 meters above the ground. Okay, so maybe there's some steps here or something. You walk up to it and you get on. And it takes 36 minutes to make one full revolution. Okay, what does that mean? Well, that gives us information about the periodic nature of this ride. Okay, so this person is going to start at a height of 5. Oh, well, that's some information right here. They get on at t equals 0, and their height equals 5 at that point. And then they go up in height, up and up slowly, faster, and then slow again until they're at the top. I guess that takes them 18 minutes. And then they descend slowly, faster, and descend slowly again until they're at 36 minutes. And then if they were to sit on the Ferris wheel, they would repeat it all over again. So what is that telling us? That's telling us that this 36 minutes is the period. The period is 36. And period, we know, is 2 pi over q. Okay, so I can solve for q. I can say, oh, okay, let's multiply both sides by q and divide both sides by 36. I get pi over 18. Q is pi over 18. So let me just lasso this and bring this a little over to the left here. So I'm going to now replace Q with pi over 18. That's because of my period. Okay. What is the amplitude here? Okay. The amplitude, remember, that is the midpoint, or in this case, the mid height, up to the max height. So that's from 100 up to, how high would this be? Oh, actually, it's not 100. Let's think for a second. We're looking at the height above the ground. This is 5. The diameter is 100. So that would mean the radius is 50. So I guess this mid height is actually 55. And the top height, I guess, would be 105. 5 to get up the ramp, and then 100 for the diameter. So the amplitude, again, is the mid height up to the max height. That's 50. My amplitude here, my A, is going to be 50. Okay, or we could see it another way. Remember that you can also get the amplitude by getting the average of the max and the min. Max plus min over 2 is the amplitude. So that would be, in this case, 105 plus 5 over 2. That's 110 over 2. That is 55. Hold up, that's a typo. Sorry. Max minus min. Max minus min. 105 minus 5. 100 over 2. That's 50. Right? And that matches what we said before. So A is going to be 50. So I'm going to put that in my equation now. All right. What else can we figure out here? Well, it's H and K that are left. I'm going to focus in on K next. Remember, K is the midline. K is this shift. So if I'm shifting up 55, K is 55. Or we could use the formula that K is max plus min over 2, the average of the two. Right? So this time we have 105 plus 5 over 2, which is 110 over 2, which is 55, right? Which matches our midline here. So K is going to be 55. We are almost done. Almost done. We just need to figure out the value of H. Well, what information is left? We've used the information about the time it takes to make one full revolution. We've used the information that it's 5 meters above the ground and that the diameter is 100. What's left is that the person gets on at time 0. They get on at time 0, and when they get on, their height is 5. Okay? Be careful now, this h here is just for height. This is not this h here. So the information I have left is that the height, maybe I should even call this y over here so that we don't get confused. Y is our height. The height is 5. Maybe I'll use another color here to show that I'm substituting it in. 5 when x is 0. When I substitute in 0 for x, I need to get a height of 5, because when the person first gets on, they're at a height of 5. Okay, and now I can solve for h. So what do? These are multiplied together. This is all the argument of the function. So I'm going to subtract 55 from both sides first. That's going to give me negative 50 equals 50 times sine of my arguments, which is 18 pi times negative h. Divide both sides by 50, that gives me negative 1 equals sine of pi over 18 times negative h. Now I want to do the sine inverse of both sides. But you know, this is a special angle, right? I know what angle I have to take the sine of to get to negative 1. In fact, if we come back to this quick picture here, we have 0, 0, pi over 2, 1, pi, 0, 3 pi over 2, negative 1, and 2 pi, 0. So in fact, it's this dot right here, 3 pi over 2, comma, negative 1. When this here is 3 pi over 2, sine of it will be negative 1. So that tells me that I need to solve for 3 pi over 2 equals pi over 18 times negative h. Okay, I'll divide both sides by pi over 18. On this side, I'll just write it like that. And on this side, when I divide by pi over 18, I'm left with negative h. Keep, change, flip. Pi's go, the 18 reduces to a 2. This expression is 27. So negative h is 27, so positive h is negative 27. All right, we found our h. So coming back up into this equation here, I'll lasso it to copy and paste. We need to replace h with negative 27. Here it is. I'm going to replace my h now with negative 27. I'll make this K in blue because it's not the most recent piece anymore. And then I can clean this up for a final solution here. I'm going to leave my Q out front. That's just fine. But subtracting a negative is the same as adding a positive. So I'm going to change it like that. Here's the equation that gives me the height of this person at any time along their ride. And if we have a quick look at Desmos, I'm going to just type this in. So I have, here we go, I have y is the height, it equals 50 times sine of pi over 18 times bracket x plus 27 plus 55. Okay, and now let's zoom out and see what this looks like. Okay, it is indeed a sine curve. Now, let's look at some key points. So 0, 5, is that a point we're expecting? Yeah, it is. That's the height at time 0, when the person first gets on. Then their height rapidly increases and keeps going up, and then kind of slows down a bit near the top, and peaks out at 18, 105. What does that represent? Well, the 18 is the x. It's the number of minutes. So after 18 minutes, they get to the top. Does that make sense? Well, yeah, it does, because we're told that the entire ride takes 36 minutes. So it makes sense it would take half that time to get up to the top. Y is 105. So after 18 minutes, the person is at a height of 105. Does that make sense? Well, yeah, it does, because we calculated that since the diameter of the Ferris wheel is 100 and the bottom is 5 meters off the ground, the top should be 105. Then what happens? Well, the person goes down slowly and then faster, and then slows up a bit near the bottom and gets to this point here, 36,5. Does that make sense? Well, sure it does. It says that the ride takes 36 minutes. Here it is, 36 minutes later, and they're back at the same height at which they started, 5. And then if the Ferris wheel were to go on again, we'd come up here. So after 54 minutes, if the person stayed on, they'd be at the top for their second time. And after 72 minutes, they would have their second chance to get off, and so on. So that looks good. Let's suppose we're asked a question. Let's suppose we're asked a question like this. Now that we've got the model, maybe we're asked to find the person's height after 8.5 minutes. Okay, so how could we do that? Well, we have two options. One, we could take the 8.5 minutes and plug it in right there and calculate. Okay, you could do that on your GDC. You could even do that with a scientific calculator. Put in the 8.5, add 27, times it by pi, divide it by 18, take the sine of that, times it by 50, add 55, and that will give you the height. So that's option 1, algebra. Well, it's not even algebra, it's just substitution. Okay, substitute that into the model that we made. Option 2, use your GDC, or in my case, I'll use Desmos, and I'm gonna say I'm gonna graph this one, and I'm also gonna graph this one, this horizontal line, and I'm gonna see where they intersect. That's the point of interest. So let's come on back to Desmos. I'll come down and graph x equals 8.5. There it is. Okay. And we can see the point of intersection right there. 8.5, 50.642. What does that mean? Well, the 8.5 is the x value, so that's how long the person has been on the ride, and the 50.642 is their height. That's the height that the person is at after 8.5 minutes. Okay, so that would be another way to solve it. Here's another possible question. For how long will the person be at a height equal to or greater than 100? Okay, you get a pretty nice view once you hit 100, let's say. We want to know, how long will this person be up there at a height of 100 or higher? Well, same thing. We could, one, use substitution. In this case, we'd be saying, look, we want the height to be 100, and we'd put that 100 right here. And so then we'd subtract 55, divide by 50. We have to do the sign inverse and solve and get in for our x. That's one possibility. The other possibility is a GDC, or I'll use Desmos here. Okay, so in this case, I'm going to graph the curve itself, and I'm also going to graph y equals 100. Why? Well, because that's the height of interest. Y equals 100. There it is. I'll hide that one. And here are the 2 points. Okay, so if I zoom in a little bit, we can see that the person arrives at a height of 100 at 15.416 minutes, and they leave the height of 100 at 20.584 minutes. Okay, so then I just subtract these two, and that tells me how long they are at that height. Okay, so they're there for, approximately 5.1 minutes, just in my head, which is a reasonably good length of time, I suppose. So a 36-minute trip, and they get to be right up at the top for about 5 minutes. That's good. So we would say our answer is 20.584 minus 15.416. That's going to be, I can't open my calculator for some reason. Okay, I'll just do it long way here. Won't take long. 15.416, subtract, I'm going to borrow here. It gives me 8. 7 minus 1 is 6. 1, 5, 3 sig figs, so 5.17 minutes. Okay? All right. So here's another question. It goes as follows. A spring compresses and expands, and its length can be modeled using a sinusoidal curve. That means either sine or cosine. That's the meaning of sinusoidal. Its maximum length is 8 centimeters. Its minimum length is 2 centimeters. It takes 2.3 seconds to go from its maximum length to its minimum length. At time 0, it is at its minimum length. Model its length. Okay, so the first question here that we have to ask ourselves is, would we like to use sine or cosine? And we can choose whichever one we like. Now, there is no right or wrong. It's more a matter of easier or harder. Remember, a sine curve looks like this. Okay, so in fact, at 0, it's halfway up from its min to its max. A cosine curve, on the other hand, starts at its max and comes down and looks like that. So the question is as to which one is easier, and sometimes they'll both be the same level of difficulty. But if we know that we're starting halfway along between the max and the min, or if we know that we're starting at the max or the min, we can make an intelligent choice. If we're starting halfway along, it makes more sense to use sine. If we're starting at the max or the min, it makes more sense to use cosine. And that's what's happening here. at time 0, it is at its minimum length. So I'm going to choose cosine for that reason. But we could solve the problem with sine. There's absolutely no reason why we couldn't. But by choosing cosine, it's going to be a little bit easier. My h value is going to be a little bit easier. In fact, it will be 0. So I'm going to go y equals a cosine q x minus h plus k. Okay, that's how I'm starting this off. Now, what I want to do is I want to flip this cosine so that it starts down low, because my problem says that at time 0, it's at its minimum length. Okay, so I want my cosine to look like this light green one. In order to do that, I need to reflect over the x-axis. So what I want to do is actually have a negative value for my a. So we have a negative a, and then the magnitude of that a is just the amplitude. So let's come back and look at our question some more. Oops, frozen here. Okay, so the amplitude, of course, is from the midpoint up to the max. And we have that this spring has a maximum length of 8 centimeters and a minimum length of 2 centimeters. So the midpoint of those would be 5, and from 5 up to 8 is 3. So the amplitude is 3. I just have to make sure that I make it a negative 3 so that I'm starting at the minimum. Okay, so we have a negative 3 cosine q onto x minus h plus k. And this h is actually going to be 0 because by choosing a negative and the cosine, we're starting at the minimum. Now we could also use the formula that, so we have that the amplitude is the max minus the min over 2, which in this case is 8 minus, what's the min? 2 over 2, which is 3. Okay, so that's just another way of getting this 3 here. All right, carrying on. K, the shift, K is just the midline, right? And we actually have a formula for that as well. Here, I'll just put an A so we don't get confused. K is the max plus the min divided by 2. It's just the average, right? The midline is going to be the average of the two. So that's 8 plus 2 over 2, which is 10 over 2, which is 5. So K is going to be 5. So far, so good. All right, now let's get Q. Q has to do with the period, right? So we have that the period is 2 pi over Q. And the period is given to us. But be careful. It takes 2.3 seconds to go from the max length to the min length. Is the period 2.3? No, it is not. Right? If we're going from the max length to the mid length, we're only traveling half the period. That's 2.3. It'll take another 2.3 to go back the other direction. So our period then is actually 4.6. Period is 4.6. So coming back down here now, we can say, okay, 4.6 equals 2 pi over Q. Solving for Q, we get that Q is 2 pi over 4.6, which is pi over 2.3. So we have y equals negative 3 onto cosine of pi over 2.3, bracket x minus h, plus 5. Okay, now I know by the way I set this up that h is going to be 0. Right? That was the whole point of getting a negative a so that we could start at the minimum. But let's pretend that we didn't know that and solve for h. Okay? To solve for h, I need to think, is there a point that I know? And indeed there is. It's found right in this sentence here. At time 0, it is at its minimum length. Okay, you'll often be given time 0, not always, but often when we're given time 0 and we can use that to solve for h. So I'm going to substitute a 0 in for h, and we're at the minimum length, which is 2. The rest of this equation is the same, and now I'll be able to solve for h. Let's put a dot here because that's as far as we got so far. So now I'm going to subtract 5 on both sides. That's going to give me negative 3 equals negative 3 cosine of pi over 2.3 times negative h. Divide both sides by negative 3. That gives me 1 is cosine of pi over 2.3 times negative h. When is cosine equal to 1? Well, cosine is equal to 1 right here at 0, 1. Okay, this is what cosine looks like. So, what should the value of the argument be in order to make this equal 1? Well, 0. So, I'm solving pi over 2.3 times negative h equals 0. Wow, we can see pretty quickly now how this gives us h equals 0 as we expected. Okay, times both sides by 2.3, we get negative pi h equals 0. Divide both sides by negative pi, we get h equals 0. Okay, so indeed, h is 0. Now, if I chose something else, let's suppose I chose sine, or let's suppose I didn't think ahead and have the negative, then I would get a different value for h that would make this all work out. Okay, so my final answer here is that y equals negative 3 cosine cosine of pi over 2.3 x, since the h is 0, there's no need to subtract anything, plus 5. That's my final answer. But you could have somebody else get a final answer that is identical and looks different. For example, I could just quickly do this right now. I hope I'm right. Y equals positive 3 cosine of pi over 2.3 x minus pi plus 5 should be equivalent to that. And a version with sine should be the same amplitude, the same Q, the same K. All that would change is the value of H. In fact, let's quickly scoot over to Desmos here and put these in. So my first equation is y equals negative 3 cosine of pi over 2.3 x plus 5. There it is. And this looks pretty good, right? It said that we started with a spring length of 2, and the maximum length of our spring is, what did it say again here? 8, okay. And sure enough, we have a minimum of 2 and a maximum of 8, so that checks out. It says also that it takes 2.3 seconds to go from max to min, so that's 4.6 for the whole period. Well, if we start here at 0 and we come down here, that looks like about 4.6 right there. Yeah, it is 4.6 comma 2. Okay, so our period's correct. At time 0, it's at its minimum length. Here it is. At time 0, it's at its minimum length of 2. Okay, so this checks out. Now, if we take the other equation that I made, come down here, I said that equivalently, and I hope I've got this right because I didn't do this in advance, cosine of, y equals 3 cosine of pi over 2.3, the same value of q, x minus pi plus 5. Let's see here. This is looking good. Oh, it's not looking that good, actually. Am I off? Oh, I am off. So, in fact, it wasn't pi. Oh, now this has got me thinking. Anyways, there is a value of h that would make this work. We could actually take some time right now and figure out what that is. All I would have to do is take this equation, let h be, let this pi make it h again, and then put in the value of when x is 0. Y would have to be 2 in that case, right? Because that's the minimum. 2 or 3? 2. Okay, so then I'd subtract over, I'd get negative 3 equals 3 cosine of this stuff, and I would get negative 1 equals cosine of this stuff. When do we get cosine equal to negative 1? Well, that happens at pi. Okay, so the argument has to be pi. So pi over 2.3, 0 minus h has to equal pi. This is where I got the pi from, actually, was this point here. I see what I did wrong. And then we'll solve for h, so we'll multiply both sides by 2.3. So I get pi times negative h equals 2.3 pi. Divide both sides by pi. So we get h equals negative 2.3. So actually what I should have put here, minus negative 2.3, that's the same as plus 2.3. Let's see if that fixes things up for us here. Bingo. There we are. Okay, so there are two different solutions to the problem. You can see they're similar, but they're different, but they both give us the same answer. And I promise you, there are several others. In fact, there's infinitely many more, and we can make some with sine as well. It doesn't have to be cosine. Okay, that pretty much gives you a nice introduction to modeling using sinusoidal curves. Hopefully that is a good introduction for you. There it is. Give you that again. This now actually wraps up the chapter, and questions on this topic can be found in exercises, just exercise 12J. Okay, then there's also the chapter review for all of Trig 2. And of course, the exam style questions. Whoops. All right.